Okay, 8-2. We are doing hypothesis testing for the difference in population means. That's mu1 minus mu2 for small samples. So, three things have to happen. Each population must be normal. Remember, with the small samples, they have to tell you that they're coming from normal populations. It can't look like the coral reef. Each sample, to be small, has to be less than 30. And the third, you can't have any overlap. You can't have some of the same people in both samples. So those are independent when there's no overlap. So each sample is independent. So no overlap. So we do the same steps as we did in the first section, except our formula is different. Well, when we read our table, though, I'm going to put that here, 4. The degrees of freedom. How did we get degrees of freedom all the way up until today? When we read our t-table? N minus 1. Degrees of freedom. Is not going to be n minus 1. So just a little note there. We're actually going to have two different formulas depending on whether the data is pooled or not. I'm not sure what pooled actually means, but they have to tell you whether it's pooled. So our by hand formula. Let's go with the easy one here. The t-score for the difference in your sample means that's what it means to be pooled, is x bar 1 minus x bar 2, mu 1 minus mu 2. So far, no difference. Bottom, also no different. Standard deviation from the first group squared over sample size. Standard deviation from the second group squared over sample size. You will use this formula if population variances are not equal. If population variances are not equal, they refer to this as not pooled data. And then your degrees of freedom, your dF, will equal either the first sample size minus 1 or the second sample size minus 1, whichever one comes out smaller. Okay, so that's the formula you're going to follow if your two variances are not equal. Now, if they are equal, the formula changes. So I can fit it on here. X bar 1 minus X bar 2. You'll love this one. The top is the same. x bar 1 minus x bar 2, mu 1 minus mu 2. The denominator is where things get a little tricky. You're going to take n1 minus 1 times its standard deviation squared plus n2 minus 1 times its standard deviation squared over n1 plus n2 minus 2. Then after you do all that, you multiply by another square root. 1 over n1 plus 1 over n2. So you'll use this formula if the two standard deviations are equal. That's called pooled. And then here your degrees of freedom will equal the two sample sizes added together minus 2. Oh, things got all kinds of complicated here. This is awful. Okay, we'll do by hand and by program and a confidence interval. Ready? Okay. Norse Pantheon. So let's go by hand first. Let's get the big one out of the way. So example 1. Okay, we've got a manufacturer and his competitor. I'm not going to write a bunch of stuff today. Yep. Okay. So I don't know what we're comparing here. Mean. Maybe it's like battery life. The mean of this guy is 73 months. Standard deviation 2.4. Sample size was 12, small sample. Competitor, the mean is 74. Standard deviation 3.2. Sample size 15. Sigma 1 squared equals sigma 2 squared. We're going to test this at 10%. Both populations are normal, and the claim being made. The manufacturer's mean is less than his competitor. Okay. So first of all, pick up on the fact that it's small sample, normal population, so we're going to be using the t-score business. So we rewrite the claim. And we want to distinguish between the two, so I'm going to go with the mean. I'll use M for manufacturer and the mean of C of competitor. And what he's saying is the manufacturer is less than the competitor. And now we write it as a difference, just like we did last week where you subtract to get a difference of the two. I'm going to choose to subtract the mean of the competitor from both sides. So the claim gets rewritten as the mean of the manufacturer minus the mean of the competitor is less than 0. There's your ha. And there's your ho. So what tail test are we going to do? Left tail. We've got alpha's 0.10 here, so 0.90 here. Because it's small sample, we're looking for a t-value. So you need your t-table. Do I have a t-table? I might have one. You guys still have your paper? You need one? You good? You want one too? Can't throw them away till June. Oh, lost it. Okay, so we're going to look up a t value, but we need to know whether our data is pooled or not, so I know what to use for my degrees of freedom. So, because I can either do n1 minus 1, n2 minus 1, or n1 plus n2 minus 2, depending on whether I'm pooled or not pooled. What am I? Pooled. It's right here is the hint to say pooled. So our degrees of freedom, according to pooled, is add the two sample sizes together and subtract 2. So we're going to add 12 and 15 and subtract 2. That gives us 25 degrees of freedom. So now we just use the t-table. Going down to 25 degrees of freedom. We've got a one tail with, what was it, 10%? So 1.316. There you go. You must have missed one on the test. No? Negative. A lot of people missed one on the test for not putting the negative in because of the being in the left tail. Okay, now we have to do our formula by hand. And guess which one I gave you? The really ugly one. Because if you can get the really ugly one correct, I know you can get the easy one correct. So we're going to follow this ugly one because we're pooled. So the t-score, and we got to go in the order we wrote our claim, so it's the manufacturer minus the competitor. So that will be the 73 minus the 74. And then the whole has a 0 in it. And then the bottom is just ugly. So it's just kind of plug and chug, follow through. Sample size minus 1. I'm just going to put the 11 down. Forget about the extra stuff. Why type all that in? So 12 minus the 1 times the s squared plus would be 14 times 3.2 squared. And the bottom, we just figured that out, n1 plus n2 minus 2. What did that come out to be? That was our degrees of freedom. That was 25. I'll just stick that in there. And then times another square root here. 1 over 12 plus 1 over 15. Definitely calculator challenging. Let's see, where do we need parentheses at? Where do we have to have them? Okay. The top, if you just want to figure out the top and put -1, then you won't need them. But otherwise, you would need this set of parentheses here. And then you would need a set here to make sure that both of those square roots get put in the bottom. I also have a numerator here. All right, let your fingers do the walk and see what you get. I don't know why this thing isn't working. explains it. There we go. There we go. Well, maybe not. There we go. What'd you guys get? Since I'm way behind. I have an answer here.
We all know that.
All right. Do we have a negative? Point? 899?
No.
Oh yeah, 898. Okay, let's see how you need a way to get through this. If you have to do it in parts, then you do it in parts. But let's see if I can do it in one line, since I'm such a big talker here. All right, 73 minus 74 divided by square root. I need a numerator. 11 times plus 14 divided by. Well, you got to close off this one to stop your first square root. And there's an extra one, and then another square root. There it is. So the extra one, because when you hit the square root, this one comes up, and you'd have to close it off after the 25. There. If not, my suggestion is to work out the top, work out this first square root, work out this square root, and then just have those three numbers that you're working with. Yeah, you can always do that. And then use another set of parentheses there. Just do the top, do the first square root, do the second square root, and then come back through again. Quit? Okay. Do it in parts. That's my suggestion. All right, so now let's try program 1. The program for these two small samples, any guesses on the program name? Considering the last one was 2SAMP Z-test. 2SAMP T-test. So let's see, we're going to compare snow tires in braking distances. We've got winter fire, and Alpine tires. Okay, mean braking distance here, 102 feet. Standard deviation, 10 feet. Sample size, 10. 94 feet. Standard deviation, 4 feet. Sample size, 12. Population variance is not equal. Populations are normal. Claim is that the mean braking distances are different. I can see 102 is different than 104, but are they far enough apart to be in the tail of the other graph is what we're checking. Is that a significant difference? Okay, so even though we're doing it by program, we still rewrite the claim. So we've got the mean of the winter fire and the mean of the Alpen tires. And if they're different, what's our sign in the middle? Not equal to. So then writing it as a difference, we'll subtract to bring it over. Matt does this all in one step. There's nothing wrong with that. That's the ha. There's the ho. Okay, that's the only thing we have to do for the by hand. Now we just run the program. So let's see what's in the program. Not program, stat, test, 2SAMP T. 2SAMP T test. Oh, this programmer was nice. They put all of the stuff from sample 1 together. So a different programmer, I'd say, did the other one. So because I wrote the winter fire first, that's going to be my sample 1. So right in order, 102. S1 is 10. N1 is 10. Let's see, 94. 4. 12. Ha has a what? Not equal to? Yep. Not equal to. Pooled. Yes or no? Right here. The not equal to on the population variances, so this is not pooled. No. Calculate. What do I want off of this screen? P. Always the probability of this sample, which is 0.036. Oh, I didn't give you an alpha. I have to give you an alpha before you can decide now. What do I have here? Oh, right there. Alpha is 0.05. So how does our P compare to alpha? Less than alpha. So what are we going to decide here? Oh, we didn't finish the other one up, did we? Oh, yeah. Well, all we did was get to that now because that was such a challenge. We'll go back and finish that one. So if P is smaller than alpha, what are we deciding here? Same thing all the way through. Reject. Small probability, probably not going to happen, so we're going to reject the ho, because that's what we tested. What does that say about the claim? Because the claim was the ha. Claim is true. Yeah, we didn't finish the other one, the two parts at the end here. Oh. Back to this one. So we've got our T table, which has 0 in the middle. We got a negative 0.89. My critical value was at negative 1.3, so we're in here. So we got to fail to reject the ho here. Making the claim, what was the claim? Was the ha again? Neat. Okay. And the confidence interval here, it's upside down. Program only. We're not doing the formula. For mu1 minus mu2 is the 2SAMP T int. Confidence intervals, the program ends in int. Okay, let's just do the one we just did with the tires. We'll just do the confidence interval for that. Then we don't have to write all of it down again. So let's just see what's in the program. So let's go run with that winter fire stuff and Alpine stuff. Get a confidence interval for the average braking distance between the two. So stat, over to tests, looking for 2samp t int. There it is, down at number 10 on mine. And what's nice, all the data's still here. Transferred it into this program also. Confidence level, let's go with 95%. Were we pooled or not pooled? Not pooled? And then calculate. So everything's there, it's just knowing what they're asking for. Is this a hypothesis test, or did it ask for a confidence interval? So this will give us the difference between the braking distance of the two tires. Feet. There it is. Okay. No? Anybody else? You did? All right, Matt. There's somebody else that did too. I don't know what you changed. Let's see, 10. Right there. 102, 1010. 94, 412.
Yep.
Then, did you leave it at 95?
Oh, no, you said .99.
And then no.
Yeah, I got it.
Okay, now we're good. I was going to say it had to be something small. All right, for your practice here. Stats. Page 395. 12 and 13 by hand. I'm sure there's one of each there. And then 15, 16, 22, 24 are all program.